Okay. Professor Tom, Professor Srinivas, shall we start? Time.
Yes, whenever you are all ready.
Yeah, I think others let them join. We are the people are here, and then some people are on online. They'll be joining.
A very good morning to one and all present. We, National Transportation Planning and Research Center, NATPAC, are organizing a technical talk series titled TransTech Talk Series. To give us an overview of this series, I invite Professor Dr. Samson Matthew, Director, NATPAC.
Good morning to all, and good evening to Professor Srinivas. National Transportation Planning and Research Center, NATPAC, is an institution of Kerala State Council for Science, Technology and Environment. It was established in the year 1976, and in 1982, it was reconstituted as an R&D center under the Department of Science and Technology, Government of Kerala. NATPAC works on multimodal systems of transportation covering road, rail, water, and air. NATPAC has creatively contributed to the development of transport sector of the country, both as a consultant and as an advisory role. Center undertakes research, consultancy, and training programs in the field of traffic engineering and transportation planning, highway and pavement engineering, planning of rural roads, regional transportation, public transport system, alternate options for transport system, water transport, traffic safety, tourism planning, transport, energy, and environmental studies. As on today, there are 22 scientists, 8 technical officers, and 7 technical assistants are working under 5 scientific divisions, namely Transportation Planning and Engineering Division, Traffic Engineering and Safety Division, Highways and Bridges Division, Water Transport Division and GAS, Information Liaison, and Training Division. Our research activities are guided and monitored by the Research Council of NATPAC under the chairmanship of Professor Tommy Matthew. Professor Lelida from IIT Madras, Professor K. Sudhakar Reddy from IIT Kharagpur, Professor M.L.R. Anjaneyulu from NIT Calicut, Dr. Velmurugan from CRRI, and Professor Ashadada from College of Engineering, Trivandrum are the other members. This particular technical talk series, the concept was conceived by the Research Council, and today we have the first technical talk. Right from its inception, NATPAC has been showing deep concern for the road safety aspect and has carried out several studies on the subject. NATPAC has been actively involved in drafting road safety programs for the state. It is also involved in providing necessary inputs in areas of accident and trauma care management, road safety guidelines, and action plan for the state of Kerala. MOU with the Ministry of Road Transport and Highways and Indian Road Congress for imparting training on road safety and safety audit. Around 60 plus engineers in 2 programs in the last 2 years. We have 7 certified road safety auditors with the NATPAC and completed more than 1,800 kilometers of consisting of national highway, state highway, major district roads, and the rural roads coming under the Prime Minister Gram Subject Yojana program. Traffic Engineering and Safety Division under the headship of Mr. Sanjay Kumar VS involved in a lot of road safety related activities, including crash analysis. PE&SD division took initiative to organize the technical talk series named as TransTech Talk Series, and today we have the inaugural function. My congratulations to Transportation Engineering and Safety Division, and especially to Mr. Sanjay Kumar. NATPAC has many social outreach programs for imparting knowledge to public and students from academic institutions. I welcome all of you to the expert lecture program, Tech Talk Series. This expert lecture is a learning event in which an expert in a particular field gives a talk to us on a popular particular topic. Our Tech Talk series is designed to provide a comprehensive exploration of the latest advances in the field of transportation. It is planned to cover a wide range of topics from different experts and leading professionals from all around the globe.
Outside,
They have
19 ladies.
extensive
She should know time. So yeah, which time?
They have extensive experience in the field and offer insights into the practical application of these technologies. It is our pleasure to kickstart the Tech Talk series with Dr. Srinivas Pulugurtha, Professor and Research Director, Department of Civil Engineering, University of North Carolina. And we have with us our Chairman of Research Council, and he is agreed to inaugurate this function. We have people around the world, like especially the faculty, the research scholars, MD students, and our NATPAC institutes, the scientists working in this area. And we expect people from the motor vehicles department of Kerala state also will join. And this series will be continued. Now our decision is every month we'll have one, and we will like to plan. We would like to organize that one on the second Friday of every month. And once again, I welcome all of you to this program.
Thank you, Samson sir. To mark the official inauguration of the series, I invite Dr. Tom V. Matthew, Chairman, Research Council NATPAC, and Professor IIT Bombay.
Good morning, and thank you for the invitation. And again, it is my privilege to be part of this TransTech series, the first one. We have been interacting with the NATPAC and scientists there, and one of the key objective of this kind of talk is to enhance the exposure of the scientist, both with academia and industry. And so this kind of talks and invited lectures will really be a very indicator of the growth of that institute. This also help basically to enhance the visibility of NATPAC. We have been encouraging them to have a national exposure, but I think great appreciation in NATPAC for going international, and that will really will enrich their exposure, and especially approaching the research in a very systematic way. And we have a lot to learn from the international community, and especially from US, and how systematically they do research. The roles are well defined, what academia will do, what industry will do. And so that's a very good model. And so these kind of interactions will help, I'm sure, NAPAC to look into ways how you can actually make a big change in the way that you conduct the research and the applied projects. Both are really very important, and you would see that, okay, from these kind of talks, how they handle systematically these things. And coming to the topic, I think on safety, I think it's a very socially very relevant, and also it's a focus area of NATPAC and as well as the state. So this topic looks at from how from a planning perspective, how we can explain accidents and model them. And if you're able to successfully do that one, that can help significantly frame policies and interventions that can reduce accidents to a significant thing. And the state of Kerala especially has a great role to play in this aspect. because of the special conditions, the road density, and various issues related to that one, that is significantly increase the accident rate. So that way, this will be a real helpful. And to conclude, this will also help mentoring or collaborations with various leading researchers also. So, so I think that will also give greater opportunity for the other researchers also to study some of the unique problems the state is facing. And so that way, look forward to this talk, and hope some lead will take from this talk, and maybe have a greater interaction with Professor Srinivas. So with this opening remarks, um, on behalf of the Research Council and on the NATPAC scientist and the team, and on behalf of the director, I would like to formally inaugurate this tech series and welcome you all, and hoping that this talk will have some tangible outcome. Okay, with this, I conclude. Thank you.
Thank you, Tom, sir. The first talk in the series will be delivered by Dr. Srinivas F. Pulugurtha. To introduce the speaker to all present here, I invite Sri B.S. Sanjay Kumar, Head, Traffic Engineering and Safety Division, NATPAC.
Good morning, respected Tom sir, Samson sir, and good evening to the most respected Pulugurtha sir and those who are present online. And so with about 1.3 million road crash fatalities occurring around the globe, and India, of course, occupying the first position with the 12% of the total crashes. The TransTech Talk series is to begin with traffic safety as the theme. So as we know, crash prediction models attempt to predict the chances of occurrence of crashes, and the present talk is addressing on the advancements in crash frequency prediction modeling. And of course, with using surrogate data such as demographic, socioeconomic, and land use characteristics. So for this particular talk, it's my privilege to introduce Dr. S.S. Pulugurtha for the talk. Dr. Srinivas S. Pulugurtha sir is currently working as professor and research director at the Department of Civil and Environmental Engineering at the University of North Carolina at Charlotte. He is, of course, a professional teacher as he's teaching graduate and undergraduate students, and is also currently the director of Idea Center at Charlotte. Dr. Pulugurtha has experience and worked in diverse fields of transportation, traffic safety, active transportation, ITS, and connected and automated vehicles, transportation systems planning, operations, and GIS. He has led and successfully completed more than 85 sponsored projects, both in the capacity of PI and co-PI. And Professor Pulugurtha is an author of more than 250 peer-reviewed publications, including 124 journals, and almost 300 technical presentations at various venues. And his accomplishments, research accomplishments, are recognized with 3 Best Paper Awards. He's a good teacher. He has mentored 21 PhD students and 58 MS students, and is professionally also active. Is a member of the including the ASCE, that is Fellow of Association of American Society of Civil Engineers, Institute of Transport Engineers, TRB, etc., etc. So, of course, my personal gratitude to Srinivas sir for accepting my invitation, because it was all on a very short notice, but I could deliver the intention to have this talk, and he's readily agreed for this. So with this very, very brief introduction, of course, the introduction which is made is very, very brief, considering the capacity of Pulugurtha sir. So let me welcome Pulugurtha sir for this particular talk. Thank you, sir.
Thank you very much, Sanjay. I hope everyone can hear me okay.
Yes, Dr. Srinivas.
Thank you. Firstly, I would like to thank Dr. Samson Matthew, Mr. Sanjay Kumar, and Dr. Tom Matthew for giving me this opportunity. And Mr. Sanjay, when you contacted me, I thought I'm doing a talk, but I never imagined doing the inaugural talk or being the first one to be part of this lecture series, but I hope it will be a very good one. And I congratulate you all on this particular step and wish you all the best with more talks related to the transportation planning and safety. As Sanjay mentioned, again, my focus is on advancing crash, this presentation is on advancing crash frequency prediction modeling using, let's say, GIS. I'm going to start with some general introduction. Certainly one point that Sanjay mentioned is, let's say, short talk at those before I'm kind of presenting on this topic. But after that, after the, let's say, initial introduction slides, most of the, let's say, information that I'm going to share, especially results tables related, are primarily from 3 different projects. And a couple of them are funded projects. One is an unfunded project, but you'll see that one of them deals with prediction, the intersection level, another one at area level, the third one at the link level. And it touches on various aspects like network characteristics ranging from network to socio-demographic, economic, and land use characteristics. Moving on to the first slide again, I want to thank NATPAC in particular for this opportunity. And I'm glad to be here. It's always a pleasure talking to Sanjay. I mean, I remember some of you kind of being at the traffic safety workshop, and I did it at NIT Surat. That was like almost 4+ years ago. So it's always good to kind of connect with you all. As Sanjay mentioned, again, there are approximately 1.3 million people that are killed annually every year. That's primarily related to road traffic, and more than 20 million suffer non-fatal injuries. So if you look at these road traffic crashes, right, most countries, I mean, it's probably equivalent or maybe exceeds like 3% of their gross domestic product. And needless to mention, you might have read in several articles that it's the leading cause of death for children and young adults. So many, let's say, nations, I'm sure including India, I mean, the primary goal is to reduce traffic fatalities and injuries, as well as enhance road safety. Now, when we look at the economic loss, one of the reasons we emphasize a lot on, let's say, the economic is because of the economic loss due to a crash, which could depend on the type of crash that we're talking about. For example, if it's a fatal crash, in North Carolina, the numbers estimated economic loss or cost of a fatal crash is about $11 million. Again, injury crash, it depends on the type of injury. Likewise, property damage only crash. The economic loss, again, if you look at some data, it also depends on the type of collision, whether we're talking about involving a pedestrian, bicyclist, or even head-on collision, angle collision, or some other type of collision. It certainly varies from one geographic location to another geographic location, certainly from one country to another country. Even within the United States, you'll see different estimates for different states, even within like an area level, at an area level, like urban area compared to rural area, again, the numbers are very different. And again, as I mentioned, again, it certainly differs by, let's say, the travel mode as well as the user. Again, there are several other factors which emphasize why we need to kind of consider, let's say, road safety as enhancing road safety as one of our primary goals. Now, if we look at as a practitioner, as a researcher, one of the problems that we kind of like always face is like, where do we want to allocate our resources, which typically depends on identifying high crash areas. And obviously you got to prioritize high crash areas for which you kind of like look at several safety performance measures. And these measures could be applied based on whether we are trying to analyze at an area level, at a, let's say, a link level, or at an intersection or a point level. And again, these are not like any new ones. There are a couple of, let's say, combined methods that we explored to minimize, let's say, the disadvantages of some of the methods. For example, if you look at crash frequency, it only takes the number of crashes into consideration, but not severity or exposure. So that's kind of like a limitation. And if you look at, let's say, allocation would be more towards locations with higher number of crashes rather than based on exposure in relation to the crash rate or some other factor. So there are bias, there is some kind of bias based on the type of metrics. So there are combined methods that can be applied, but these are typical, let's say, safety performance measures, crash frequency, equivalent property damage only crash, where you are giving higher weight to severe crashes. Likewise, crash density could be divided by length or could be divided by area. Likewise, you can also look at crash rate. Now, if you look at additional safety problems that practitioners and researchers are interested, we're also interested in understanding the cause of the crash. Like, what is the cause of the crash? What is the contributing factor? Because we kind of like, as an, let's say, engineer or a planner or a scientist, I mean, we believe that if we understand the cause, we can probably fix the problem, right? I mean, prevention is better than cure. So understanding the cause of the crash is very important. That would also help us identify suitable countermeasures and implement them in the real world. And these countermeasures could be engineering-based, education-based, or enforcement-based. But once we, let's say, install a countermeasure, oftentimes we want to know whether that particular countermeasure is effective or not effective. So evaluating the effectiveness of countermeasures is very important because that helps us, let's say, whether we would want to install at more locations or not. And that's where the crash modification factors comes into the picture. I mean, the crash modification factor is, let's say, less than 1. You're saying that it's very effective, but at least it reduces the number of crashes. The treatment helps reduce the number of crashes. But if it's greater than 1, it kind of like results in an increase in the number of crashes. Now, another aspect that we are interested as a practitioner or a researcher is like from a proactive approach. I mean, I'm one of those who always kind of have been looking at, let's say, safety not as an afterthought. I mean, I want to see if we could understand what's causing safety problems, how we can, let's say, address these safety problems in a proactive manner rather than like once you see there are 10 crashes at a location, let's go do something. I mean, instead of let's go do something after having 10 or 15 crashes at a location, can we do something in a proactive way? So when you're looking at, let's say, the last two aspects, again, the crash frequency prediction models play a key role, and you can call them safety performance functions or crash frequency prediction models. But both evaluating the effectiveness of countermeasures and proactive planning kind of like require looking at or developing or using some kind of crash prediction or frequency prediction models. And if you don't have good data, I mean, my mindset or my thought process is that you could also apply the same process for, let's say, crash conflict prediction models. If you have, let's say, a means or mechanism to kind of accurately estimate conflicting situations that are an indicator of your potential safety issue or crash frequency. Now, the prediction, again, as I said, could depend on the geographic unit, whether we are trying to predict crashes at an area level, at a link level, or at an intersection level, or at a particular point in your network. Again, you can also develop models specific to fatal crashes, injury crashes, or PDO crashes. You can also develop, let's say, models specific to collision type, like vehicle-only involved crashes, pedestrian-only involved crashes, or bicyclist-involved crashes, or even based on collision type, like head-on or other types of, let's say, collisions, angle collisions, and so on. Now, to me, the very simple, let's say, crash prediction model could be like your crash frequency, right? Based on the crash frequency, using your time series, let's say, analysis, you could predict the number of crashes that could potentially occur. Could be the simple, like, average number of crashes that potentially could occur every year. But over time, we realize that, let's say, the data may not be linearly related to, let's say, year or some other, there is some kind of randomness, and that could lead to non-linearity. And that non-linearity, again, kind of pushes us to look at not linear, let's say, regression models, but maybe con-based non-linear regression models. You could also look at, let's say, the second basic one, right? Even, let's say, when we are talking about crash rate, if you are computing average crash rate at a particular point, or for an intersection or a link, that crash rate, again, could be a, let's say, predicted value or expected number of crashes, right? That could be a simple one too. And it could be linear or it could be non-linear in nature. Now, when we look at these two, we got to be careful with the data, right? I mean, if you're using longer period data, I mean, there could be some aspects that may have influenced, let's say, the number of crashes at a location. Sometimes if you have a lot of crashes for a random reason in a particular year, that could kind of have an effect on, let's say, the mean, especially when you're looking at shorter periods, but maybe not so much when you're looking at longer periods. But in general, when you're looking at this time series example, or when you're trying to predict crashes, I mean, the first thing that comes to researchers or practitioners' mind these days is how to kind of like address the regression to mean phenomenon. Now, again, that regression to mean phenomena typically is applicable when you're looking at before after. That again, even in the before after scenario, the difference is not primarily because of the treatment, but some other random aspect. So before and after crash frequencies would, to some unknown degree, not be attributed to the treatment, but to the regression to mean phenomena. And that might cause the perceived effectiveness of the treatment to be overestimated. So that's the reason, again, you got to keep, let's say, the regression mean aspect in mind when you're trying to predict, let's say, crash frequencies. Now, in US, again, when you're looking, when you look at like crash prediction, again, the first thing that we try to look at is highway safety manual. And if you look at this highway safety manual, that's where you'll see both, I mean, mostly like safety performance function as a term. And when we look at data, in general, crash data is considered to be, let's say, over dispersed. I mean, basically the variance is greater than mean. And the highway safety manual discusses both methods and models that can help you estimate the number of crashes, say, for example, at an intersection. The general form of, let's say, an SPF or a crash frequency model, in this case, for predicting the number of crashes at an intersection, depends on the major street, let's say, traffic volume and the cross street or the minor street traffic volume. So you can see that, Ellen, again, we're kind of looking at it more from nonlinear, let's say, relationship perspective. And A, B, C are your regression coefficients. So you could use this, let's say, the models that are available in there. And this is an example, like SPFs that are available in highway safety manual that were developed, I believe, from, let's say, the state, using data from the state of Washington for two-way stop controlled intersections. And maybe others too, based on data from other states as well. But again, you'll see that, let's say, they have models. When you look at two-way stop control intersections for rural areas, for urban suburban areas, again, you could argue saying the characteristics of urban suburban areas are very different. So let's develop models separately for urban suburban areas. And you can see you have models for four-legged intersections as well as three-legged intersections. You also notice from the table that you have models for estimating the total number of crashes, fatal and injury crashes, and PDO crashes. I mean, and sometimes we kind of try to look at fatal and severe injury as one category, but injury type B and C, which are minor injuries, as kind of like a different category. So you can see the intercept, the coefficients for major street, coefficient for minor street, and let's say the over dispersion parameter at the last column. And if you were to simply pick an intersection, for example, in a rural area, and you're trying to use this, let's say, the information in this table. For example, you can see that for rural four-legged intersections, the safety performance function or crash prediction model, it will look like is equal to like e power minus 8.56 plus 0.6 times ln of ADT on the major street plus 0.61 times ln of ADT on the cross street. Likewise, based on, let's say, other characteristics like number of legs, area type, you could pick other, or you could pick models or coefficients specific to, let's say, fatal injury crashes and PDO crashes. Now, the estimated number of crashes in this case, that the crash frequency, in most cases, is not going to be equal to, for example, whatever you expect. So that's the reason, again, we try to calibrate, let's say, the models. HSM, let's say, certainly recommends calibration of your safety performance functions. In this case, what we try to do is compare the observed number of crashes with the predicted number of crashes at some sites, and we develop this calibration factor. And this, let's say, account for both spatial and temporal. As I said, the data that was used to develop the models in the previous slides come from other states, and if I want to apply it to North Carolina, it may not be 100% applicable, right? I mean, so you'll certainly see some factors, either study area specific or temporal aspects, that will certainly have an effect on your estimates, and you want to take into account those aspects, and that's where your calibration factor comes into picture. So this slide again shows highway safety manual, like let's say SPF calibration factors for four-leg two-way stop controlled intersections that kind of like is more specific to North Carolina. What we did in this case is we looked at like 57 reference intersections, basically two-way stop control intersections. We collected the data. We looked at, let's say, data each year separately from 2011 to 2019. And we looked at the total number of crashes. Number of crashes per year is 90.77, and the average number of crashes per intersection is like 1.59. So if you look at the table, I mean, the figure to the right, to my right, again, basically the figure shows the calibration factor ranges from anywhere from 1.66, a minimum of 1.6 to a maximum of what, 2.54. And it varies from 2011 to 2019. So it's like, it also tells us that, let's say, you could expect, let's say, your model to underestimate, because I mean, in this case, our calibration factor is 1.66. So you need to, let's say, multiply. That means the error is pretty much like anywhere from 66% to like more than 150%. So that's kind of like the error that we're talking about, that you could expect when you're using SPFs that are coming from the highway safety manual. That's the reason we would want to kind of look at the calibration factor. So just keep in mind the calibration factors kind of are, let's say, very high, like 2, and that needs to be taken care of. Now, these are calibration factors, let's say, for the total number of crashes. Again, this is for a project that we did where we wanted to evaluate the effectiveness of converting two-way stop control intersections or always stop control intersections to mini roundabouts. And these calibration factors are more specific for the analysis where we looked at converting two-way stop control intersections to mini roundabouts. And I'm not discussing about before-after evaluation of the mini roundabouts, but I'm just focusing on, let's say, the crash prediction models, safety performance functions, and the calibration factors. And if you look at the calibration factors, they could underestimate or overestimate your crash frequency. I mean, in case of North Carolina, I mean, you'll see that they're kind of greater than 2 or greater than 1 for four, let's say, four-legged intersections. But in case of three-legged intersections, they're kind of less than 1. But most of the time, if you look at for others, again, generally they seem to be, let's say, greater than 1. So you got to keep in mind the calibration factors suddenly may indicate that your SPFs could, let's say, underestimate or overestimate crash frequency. So that's where, I mean, one of the things that not only HSM, but I also am a strong, let's say, proponent of, let's say, using jurisdiction-specific SPFs. So develop your own safety performance functions or crash prediction models that are very specific to your study area, rather than relying kind of on, let's say, crash prediction model developed by someone else. And in this particular case, for always stop control intersections, SPFs are not available. In some cases, they were not available for always stop control intersections. For the mini roundabout before-after study, we had to develop our own always stop SPFs or crash prediction models for always stop control intersections. So again, SPF, again, the HSF certainly recommends developing, even the SPF development guide suggests you to develop your own jurisdiction-specific SPFs, except that it's an data-intensive process. And when you're developing your crash prediction models, you try to use a minimum of 3 years worth of crash data. That's actually recommended for SPF development. But you also have to note that the effectiveness of a countermeasure may vary based on whether you're using calibrated highway safety manual based, let's say, SPF values, or your own developed jurisdiction-specific SPF values. And that's something that we observed as a part of the study. I'm not going to go into the details, but you would get different results. I mean, even, let's say, for the same data that was used for analysis. So this slide shows the prediction models for always stop control intersections. So we kind of like collected data. As you can see, it's not specific to North Carolina. We kind of looked at, let's say, intersections in 8 different states, but we only looked at always stop control intersections in 4 states. So those are the 4 that you will see on the screen. The intersection type is always stop control. You see the intercept. Since HSM recommends, and we were using only major street ADT and minor street ADT for two-way stop control related analysis, we only picked traffic volumes on the major street and minor street for our model development. And we kind of looked at the over-dispersion parameter K as well as AIC, archaic information criteria, and the corrected archaic information criteria. Most importantly, if you focus on, let's say, the last column, the mean absolute deviation, these these are kind of very relevant or related to your calibration parameters. And these indicate that, let's say, the values are much lower. Like we kind of like see 1 point, let's say anywhere from 1.12 to 1.33, not suddenly like 1.66 to 2.54, like in the previous case. So at least this tells us that you may be able to get, let's say, better prediction, your predictability is suddenly better when you're using your own jurisdiction specific, let's say, performance functions. So when you look at, let's say, this model development, the study locations and data are very important. The sample size should be very large. Say, for example, for the previous 3 or 4 slides, we used data from, again, as I said, 8 different states, 650 plus intersections that were used to calibrate and develop models. That's a lot of information. And actually, we captured a lot more data rather than just traffic volume and crash data. And your selection of these study locations, if you're doing before-after analysis, you want to make sure that they're very similar in characteristics to your treatment site. That's, again, another challenging problem. And obviously, availability of crash data and traffic data is also challenging. That's where, again, I've been also using surrogate data, like road network, land use, demographic characteristics for, let's say, estimating number of crashes, because, these are the characteristics that are that influence your traffic volume and trip patterns in any let's say, city or town. So this proactive planning and crash frequency prediction models, again, when you look at this particular part, could be associated because we are looking at, let's say, using socioeconomic demographic characteristics. It helps us if you're able to use the results back, tie them back into, let's say, your land use planning, transportation planning, you may be able to proactively, let's say, incorporate safety into the planning process. So here, you define the problem, you identify the data elements, you have to develop your databases. One of the things that we have been doing is like examining the correlations and selecting suitable distribution, and then developing your models, then following it with validating the models. Because once you develop the models, you want to make sure your models are able to predict the number of crashes accurately. Again, this is a different project. Here you can see that it's data specific to modeling bicycle vehicle crash frequency. That's the example that I'm talking about, the paper or the project that we did here. The data we looked at include crash data, again, traffic volume data, land use, socioeconomic, demographic, and road network. Now, one of the things that we have been also exploring is we really don't know what should be the ideal influence area or the buffer that should be used to capture geospatial characteristics. So should it be 0.5 miles, 0.5 miles, 1 mile? In other words, if you're looking at it in terms of kilometers, do you want to look at it as like 300 meters, 500 meters, 1 kilometer? There is nothing that's available out there that's widely considered as an appropriate, let's say, buffer width. And you don't want your buffer width to be too small, because then you're looking at point level data capture. You don't want it to be too large, because your influence area, again, may fall in different, let's say, data point, buffers within different data points, different data points related influence areas. Oftentimes, we also divide, not oftentimes, almost all the time, we divide our database into, let's say, 2 different sets. We use 75% for modeling and about 25% for validation. In this particular study, we kind of like define intersections, but bicycle vehicle crashes are very, very rare. So we try to look at crashes within a proximal area. So, and we only identified 100, probably 6 such locations that do not overlap much. And we divided those into 2 sets. One is kind of like about like 75, 80 locations for modeling, and the remaining 20 or so locations for validation purpose. Again, I'm not going to read, but this is just to give you a feel for the list of independent variables that we explored in this particular, let's say, research, I mean, you'll see that they include network characteristics. The one that's highlighted again, several central line miles. Again, I remember Dr. Matthew said one of the challenges that's out there in Kerala is dense road network. So you want to kind of take density related aspects like road network. That's what pretty much we are looking at. Ideally, you would want to look at not central line miles, but central lane miles, lane miles. Because when you're looking at central line, you're only looking at just like link, the length of the link. But your link could include like 2 lanes or 4 lanes and in each direction or even more. So you would want to take that aspect into consideration if it's available. So likewise, with land use characteristics. But then again, when you have so many variables, I mean, developing a model, giving it a practitioner, I'm sure practitioners would not, let's say, prefer, and it also does not probably make too much sense because a lot of times you'll see correlation between, let's say, the variables. So for example, first thing we try to check is the, let's say, variable correlated to the number of crashes. That's NC, the row that you see on the top. In addition to that, we also see they're correlated to each other. For example, in this case, if you look at the bottom small table, population is correlated to mean household income. So we don't want to consider both of them for modeling. We'll only consider population, which is relatively easy to, let's say, capture from our GIS databases, and mean household income sometimes is a little challenging and also questionable. So it requires a different process. So you could kind of, let's say, use such judgment to pick one out of, let's say, the correlated variables. But again, you could also ask a question, I mean, why only population, why not mean household income or some other variable when you're eliminating? So we normally try to develop multiple models. That's what we did in this case, like model 6 different models. And looking at the correlations, we try to pick different sets of variables for 2 reasons. One, we want to see what model would be the best to predict the number of crashes, but we also want to maximize number of variables that potentially could influence the number of crashes and see how they're kind of like associated. Is there a positive association or a negative association on, let's say, safety? So basically, we kind of develop multiple models. Then again, we test the distribution. As I said, typically your mean and standard deviation or variance will tell us whether the data is over-dispersed, variance greater than mean. So in this case, we said it's over-dispersed. If they're equal, we tend to go with Poisson. Sometimes we have explored gamma type log-link functions, but most of the time it's been negative binomial log-link function that seems to be a distribution that seems to be most appropriate for crash frequency prediction. And this is just general form of, let's say, a generalized linear model. Again, based not negative binomial log-link based distribution based model. You have the coefficient and constant term equation for each and every variable. And as I said, the goodness of it, again, they're based on the type of GLM that you use. You may be using AIC, AICC, quasi-likelihood under independence model criterion, QIC and QICC. A lot of times we adopt like backward elimination. So basically, once we select 10 or 15 variables, we include all of them in the crash frequency model. First, we then identify the one that has the highest, let's say, significance value that's not kind of, let's say, significantly related to the estimate. Then we kind of eliminate that, rerun the model until we make sure that all the variables in the model have a p-value less than or equal to 0.05. I mean, there are sometimes you could argue you could do by incorporating all the variables because there it's not the accuracy, but you want to make sure that you're kind of like incorporating other variables because that will help you, let's say, assess the association between each variable and your crash frequency. But again, typically we use backward elimination because we don't want a model with 20, 25 different variables, or sometimes even more. We just want a model maybe with 4 or 5 variables that can help us accurately estimate the number of crashes. So you'll see the 6 different models. Again, if you see a blank cell, that indicates that that variable is not statistically significant. So it was eliminated during the backward elimination process. you'll see the p-values that are in the table are always less than 0.01 for all the variables. And we also looked at deviance, Pearson chi-square, but more importantly, AIC, AICC. We want them to be as low as possible, and we want AIC and AICC to be as close as possible for the model to be a good model. Again, you can also argue 490, 500, maybe not a big difference, right? That's a possibility. So, but again, at least we can say that there are two models that seems to be good. All of them are not too bad, which is probably not a bad, let's say, indication saying that our process is reasonably okay. But then we followed up with validation of models. So for example, we looked at mean absolute deviation, root mean square error, mean absolute percent error, and mean standard error. And again, I like looking at several of these because if you're using RMSE, you won't be able to tell, for example, if your model is overestimating or underestimating. Likewise, your mean absolute deviation will not tell you whether your model is overestimating or underestimating. However, your standard error, I mean, kind of like some of them might tell you whether your model is overestimating or underestimating. So that's the reason I like kind of looking at multiple validation of model equations or models. So we kind of validated all the models, 6 models, and you can see model 1 and model 3 seems to be kind of like okay from, let's say, the values that we got for MAD, MSE, RMSE, and so on. So lowest for model 3, again followed by model 1. You'll see that model 1 and 4 seem to underestimate the number of bicycle vehicle crashes, while models 5 and 6 seem to overestimate the number of bicycle vehicle crashes, basically crash frequency. So at least it gives us some idea which model overestimates, which model underestimates, and so on. Another aspect that you would want to kind of like say observe is your model applicable to all the, let's say, locations. So you would want to look at residual patterns in bicycle, for example, crash prediction, vehicle crash prediction. So we kind of developed this, let's say, GS map and did spatial correlation. When we looked at Moran's index, the z-score, and the p-value. I mean, basically, what we observed, we want to make sure is there is, let's say, no correlation. We have to know spatial correlation between the residual of each model. Again, you can see the note. The Moran's index value close to +1 indicates clustering, while Moran's index value close to -1 indicates dispersion. Again, in case of, let's say, close to 0, I mean, it's not much, no correlation at all. But if you look at the map to the left, I mean, you see there are some points with, let's say, kind of like there are larger dots, there are others that are kind of smaller. And the difference is because the residuals, right? I mean, which indicate our ability to predict. Obviously, if it's a smaller, let's say, size dot, I mean, it's predicting close to what exactly you see in the real world. But the larger the dot, I mean, or the size of the dot, you kind of know that, hey, the model is not applicable. I mean, it's not predicting kind of like anywhere close to, or at least like it's significant. The errors are very high. So, and those errors seem to be more kind of like in the core urban area. But when you look at the suburban, or let's say let's outside the core urban area, like CBD type area, I mean, the predictability seems to be very different, I would say better. And there are obviously some locations outside the CBD area, the core urban area, where kind of the predictability is not so good. So that also, let's say, told us that maybe there are other approaches, and that's where we started exploring geographically weighted regression models for crash frequency prediction. So this is again a different project. This is in this case, our objective was to model a teen crash frequency. As you can see in the bullet, the first bullet, we used land use, demographic, socioeconomic, and road network variables, because these vary over space. Your, let's say, association with the crash again suddenly would also vary over space. An explanatory variable may be significant predictor, maybe in one area, but may not be a significant predictor in another area. And we would want to capture those variations by generating a regression model for each point individually. That's the goal here. So if you look at the GWR, so the data, again, next to the prediction location is basically going to have a higher influence on the estimation. So you have to define what should be your bandwidth. I mean, how many number of points or how far do you want to go from your, let's say, actual location? And obviously, you don't want it to go too far. I mean, like for example, 5 kilometers or 10 kilometers. Again, depends on what you think would be the ideal bandwidth or optimal bandwidth. So you need to first define that, let's say, bandwidth. So your influence is described by the weighting function, and typically it's a, let's say, nonlinear function. And as I said, you got to define your bandwidth either in terms of distance or in terms of the number of neighbors or the number of points within vicinity that you would want to use for your model development. Again, we are using GIS software here. We're not doing it manually. I mean, you could do it. I mean, if you have some other mechanism to develop your own model. So as I said here, our objective is to evaluate the effect of road network, demographic, and land use characteristics on road crashes involving teen drivers, and to develop geospatial models. And obviously, we want to compare the predictability of, let's say, both GWR-based local models and, let's say, the negative binomial global level regression model. So when I said global regression model, it's data for the entire study area. Whereas when we are saying local model, that's like based on the GWR, we are picking neighbors that are very close to a point of interest and developing a model for that particular point of interest. So again, our study areas, again, Mecklenburg County, all these studies are very specific. The last one and this one are very specific to Charlotte region in Mecklenburg County. The data, again, as I said, road network, demographic, and land use characteristics. We kind of try to look at the spatial distribution of crashes, how they're being kind of varying, basically a simple hotspot type analysis. So we kind of looked at, let's say, the train crash frequencies high at roads near schools, commercial areas, some of these areas. And that's because, again, a lot of, let's say, teens can drive their cars when they're in 11th grade, 12th grade, and kind of like they're also kind of like hang around in commercial areas, likewise like gymnasiums, sports centers, and so on. So you can kind of like observe how they've been varying over time using this hotspot analysis. You can also identify where they're kind of high, whether they're kind of like oscillating or they're not kind of changing over time, and so on. But our primary objective is, again, more on the crash frequency prediction, comparing the global level and the local level models. So we considered, let's say, the road segments. You can see, again, very similar. We kind of broken, let's say, converted the data set, broken down into two different modeling, let's say, data set and validation data set. Again, pink, purple type color links. Those are your modeling segments. The black ones that you can see on the screen are your validation segment. And we used, let's say, crash data for each geospatial analysis. We did geospatial analysis to identify crash data, identify traffic volume closest to, let's say, where we want to develop data for each and for that particular link. We also captured demographic characteristics and land use characteristics. Again, you could use what they call like circular buffers, or you could use network-based buffers. I mean, a lot of times we argue saying network-based buffers are more accurate, but there are also some research findings that indicate that maybe you may not see a significant difference between network-based buffers and Euclidean-based circular buffers. But let's say this slide summarizes the models. The first one, again, you see the variables. We kind of use the same correlations. We identified selected variables. We try to keep the same variables for the global level and the local level models. We used backward elimination. But again, at the end, we kind of came up with, let's say, these 5, 6 that we thought are very critical, so that we kind of retained in the GLM, that global level one, we kind of kept them in the, let's say, local level models. So you can see, for example, for number of households, the coefficient is For 25% of the locations, it's 1.41, and for 50% of the locations, it's 1.853. So basically, that tells that your coefficients are lower than 2 for at least 50% of the locations. The mean is 1.857. But again, they are also higher for, let's say, greater than 2.3 for, let's say, 25% of the locations. So you can see that coefficients vary for just one variable. I mean, from one let's say, model for one point to another point. So again, it's important for you to understand that, because that tells you, let's say, how important it is for, let's say, capturing data, geospatially varying data, and incorporating that into the modeling process. So to kind of visualize, let's say, the same, if you look at the very first one, that shows the number of, let's say, households. I mean, the coefficient for number of households, or the number of households, are more, let's say, predominant. At least they seem to be a critical variable. At least they're greater than 2.25, right? Red, kind of like you can see them in the southern part of the Charlotte region, or the Mecklenburg region. On the other hand, if you look at AADT is kind of like more in the core urban area. I mean, like it's in the central part of, let's say, the study area. On the other hand, if you look at number of students, high school students, that's kind of like, if you look at based on the coefficients, that seems to be more playing a very, let's say, significant role, or higher role, kind of in the northern part. And if you look at commercial area, that's kind of more to, let's say, the western part of the study area. But let's say both not kind of like southwestern part of, let's say, the study area. So you can kind of see that, let's say, the coefficients vary geographically. At some places, they're kind of like not even noticeable. In some cases, they're kind of like nominal to, let's say, in some cases, very significant. And your spatial distribution of coefficients tells us that, let's say, these models probably are better, and they will capture the spatially varying characteristics and help with better model prediction. So to summarize, I mean, the evaluation, I mean, I would say we started off with traditional linear models. We started looking at, let's say, normal distribution, kind of like as an assumption, right? Constant variance, but we kind of like felt that that's inappropriate crash frequency modeling, because obviously you're talking about count data, the response is a count. So we started looking at nonlinear model. So because we are modeling, let's say, counts, like negative binomial, log normal, gamma, Poisson. But then again, we kind of like feel that they're often spatially heterogeneous, and you need to take that heterogeneity into account. And that heterogeneity, the variation is influenced by the spatial aspects in the data. That's the reason, again, geographically weighted regression models could kind of like, which can accommodate that spatial heterogeneity and can capture local details more accurately, would be more applicable. So whether you're looking at geographically weighted negative binomial or Poisson, again, that depends on, of course, the distribution, the data distribution. So this is, again, what we have been kind of like doing. I mean, you could see that we kind of like use just like traffic volume for model prediction. We have used surrogate data, developed statistical models, but also geographically varying, geographically weighted regression-based models. We recommend developing and certainly using jurisdiction-specific crash frequency models rather than calibrating crash frequency models that are available out there from other jurisdictions. And if you have the resources on the data, I mean, certainly recommend using GWR, because your GWR accounts for spatial variations and has better predictability than GLM-based models. The only problem that arises with, let's say, GWR is your sample size, and your sample size has to be geographically distributed. Needless to mention, again, we're talking about data, a lot of data, right? For model development, for year-wise calibration, quality of the data. Now, that's always challenging. I mean, even in the US, I mean, there are some, let's say, aspects of the data that we feel very good about. There are some that we don't feel very good about when it comes to the accuracy. Again, it all depends on the resources that are required to, let's say, collect the data, capture information at the site. We're also exploring machine learning and other similar methods and comparing with GWR and GLM based methods, but that's kind of like still work in progress. That's pretty much what I have for my presentation, and I'd be glad to take any questions, comments.
Thank you, Srinivas. Now there are some questions. This is a question and answer session. Yeah.
Sure.
The first question was how to find out the optimal bandwidth.
That's typically, I mean, it's a trial and error procedure, but you kind of have the option in the GIS, let's say, to set your values and you play around and you can identify. But typically, to me, I mean, it's your optimal bandwidth. You have to use some engineering judgment too, because you don't want your bandwidth, even though it says optimal, you don't want it to be, let's say, too high. You want to take, let's say, the characteristics, especially if you are familiar with the study area, right? So, for example, if your optimal bandwidth for a study area that's primarily in residential includes commercial, you know that the commercial area characteristics may not have the same kind of effect. I mean, you don't want to include, let's say, even those kind of points. So you got to use combination of your engineering judgment, and obviously it's kind of like a simple technique in GIS, but you would use typically a trial and error procedure for that.
That was the
I don't
question
know if
from
someone had a comment or they were kind of having a follow-up question. Heard something, but not sure.
Okay, that is a question from Asha Lakshmi. The next question was from Ali Hussain. How would this analysis work in the Indian context where the accident data is limited and deficit in terms of being detailed?
That's a very good question. Again, and I know that suddenly I know that would come out as a question because, I mean, the quality of the data. But I would say this is what you need to take to, let's say, your upper level officials and emphasize the need to collect quality data. But at the same time, as I said at the beginning, I mean, this is crash frequency prediction model, but if you're able to at least like one way or other using either trajectory based or kind of like video data trajectories or something of that sort, if you're able to collect data, right, at different points and quantify conflicts, you could also apply, let's say, the process for crash conflict prediction. I'd say not crash conflict, but conflict prediction model. If that makes sense. But again, quality data, again, that's very important. I mean, the only thing I can think of is like, instead of relying on crashes, I mean, maybe start capturing, let's say, sample video data, identify conflicting situation, and start at least like looking at conflict prediction. But at some point of time, you would want to do a study correlating your conflicts with the actual number of crashes, just to make sure that they are kind of like correlated to each other. Otherwise, you'd start questioning conflicts, because I mean, I've seen some studies where they said they two are correlated. Some they said that they are not correlated.
The next question from Mehrab Nazir. Since you have compared GLM-NB with GWR, can you please explain how you accounted for the spatial correlation in GLM-NB?
Spatial correlation in GLM-NB. Trying to understand what, basically when the GIS software, the way it takes itself is like it will, once you define the number of points or the distance based, right? The optimal bandwidth, you pick all the points, and the way it does is like it's going to develop a model, GLM based NB model using, let's say, data for those points that are within that bandwidth. So again, we're not doing it manually, but the spatial variations are kind of taken care of when you are defining the bandwidth itself. But the NB does not, when you're developing the, let's say, actual NB model, it does not. Basically, just imagine you're developing multiple NB models, right? NB model for different parts, different links in the study area.
So next question from Shalini PN. How do we decide on the weightage to be given to the different geospatial or road network related parameters by using GIS tools?
That's a good question. Again, we never try to give different weights. But again, what we try to do is look at the correlation so that if they're correlated, we are not trying to, let's say, duplicate the effort, or we're trying to minimize, let's say, the collinearity or the redundancy type issues. But we never try to. Again, the weightage normally would come in the form, to me, like in the form of your coefficients, right? That will kind of give you a feel for how significant. But a lot of times, we're not saying that we're going to give more weight to road characteristics, not so, let's say, higher weightage for, let's say, land use characteristics and so on. That's a good question. I never thought about it, quite honestly.
So next question from Asha Lakshmi again. In a place when we consider a long time due to the development in surrounding place, whether we consider the same area as considered in previous years for comparison, or we decide the area based on the land use, demographic characteristics, etc.
We have used land use, let's say, characteristics, but again, you got to be careful. For example, if you are trying to develop a model for, let's say, 2020, and the development was started in 2021, you don't want to take that even though your land use data has that as a part of your development. Ideally, you would want to take, here they use the word like floor area or heated area. Maybe you want to look at like the total floor area because you may have multi-story building, right? So you want to know the square footage or whatever is the, let's say, built area. But basically look at, let's say, when it was completed. Again, that's where the quality of the data comes into the picture. But again, if you don't have those details available, it's challenging to kind of like look at some of those limitations. But in our case, we kind of look at when it was built, what kind of study area are we looking at? Does it make sense to kind of look at, let's say, the land use, different land uses within the buffer based on when they were built, so that we're not kind of looking at something that does not exist in the population.
So one more question is there from Ishan. Out of the collected data, which would be the most ideal percentage for dividing the data set for modeling and testing?
Typically, 75-25 is what we have been, what the literature says. But again, if you have very large data sets, you could do that. And again, you would also want to select, let's say, data sets randomly so that you're not, let's say, having any bias in the selection process, right? So oftentimes what you do is you randomly select 75% of the location, but you may also want to try develop a model using a different, let's say, randomly selected 75% of the locations, so that you can kind of check how significantly different or how different or not different. You want to check the sensitivity aspect, but 75-25 generally sounds kind of like a reasonable split between the modeling and the validation data set.
So next question from Parth. How do we decide the buffer zone around a road network if we want to take the population around the road as an affecting variable in our model?
It's a good question. I wish I have a definite answer, but I'll share some that we try to, let's say, apply different rationale. For example, when we try to look at pedestrian crashes, modeling pedestrian crashes, most times people, we don't expect them to walk for more than 5 minutes, maybe 10 minutes, let's say. So our limit was more not look for more than maybe 5-minute walking distance. In terms of a 10-minute walking distance, which in terms of like, which here is like approximately based on average walking speed of 3 to 4 feet per second. You're looking at not more than half a mile. So that's basically what, 0.8 kilometers. So about 400 meters. If you want to kind of like look at like within, but for vehicles, it gets a little tricky because for a different, let's say, problem for modeling traffic volumes, we try to look at different buffer widths for different types of road classes. For example, if you have a major highway, I mean, your major highway may attract traffic from, let's say, even 10 kilometers, within the vicinity of 10 kilometers, right, or 5 kilometers. So you would want to have like a larger buffer width. But on the other hand, when we are looking at collector roads or minor roads, minor arterial type roads, we try to look at like 1.5. So most of the time, unless it's like a interstate freeway or a major highway, we try to not look at more than, I would say, 1 to 2 kilometers. So roughly 1 mile, 1.5 miles, 2 miles, kind of like 1 to 2 kilometers is what we were focusing on for typical urban roads. Again, the assumption there is that only it's not that only people in the 2 kilometer buffer would use that road. I mean, but majority of the traffic would one way or other be related to, let's say, origins or destinations within that, let's say, 2 kilometer buffer. I mean, at least we are able to explain majority of, let's say, traffic related aspects or traffic contributing factors. So you got to use some judgment there. I mean, what we have tried to do is like for pedestrian related, we tried 0.25 miles, 0.5 miles, up to 1 mile, and then decided based on, let's say, what the variables of sign, how meaningful they are, and let's say something of that sort. I mean, most of the time, looking at these model predictability in addition to the coefficients. But for traffic related, we have used anywhere from 1 mile to even up to like 3 miles. In some cases, we tried 5, but most of the time, we felt that 1 to 3 miles should be adequate for capturing geospatial data. Bicycles, maybe about a mile. They certainly would kind of like travel longer than, let's say, people who would want to walk. So some kind of a judgment there. I mean, it's what we have used, but you won't find, I wish, a widely accepted, let's say, recommendation saying that this is what would be applicable.
I think, Srinivas, I think no further questions. Somebody would like to again share, lesson probably they can share that and with given, so they can continue to interact later also. So.
Thank you, Srinivas sir, for the wonderful session. Now I invite Sri Ebin Sam, scientist NATPAC, to deliver the vote of thanks.
And crash prediction models, as we all know, are very much significant in the safety planning exercise and provide solution to the road safety problems. In this context, NATPAC has a plan to organize a Tech Talk series, and Dr. Srinivas Pulugurtha, in midst of his busy schedule, he was well accepted our invitation for the inaugural talk of the Transport Tech series organized by NATPAC. We are very much thankful to Sir. Sir has detailed about the development of safety performance function, its calibration, and also highlighted the significance of localized SPF, safety performance function, and also explained the statistical procedures involved in the traditional models, as well as the importance of geospatial models. It was a quite enlightening for the researchers, the participants who attended this online talk series. I would like to, on behalf of NATPAC, we would like to thank Dr. Srinivas Pulugurtha for the insightful talk. I would like to thank on behalf of NATPAC, Dr. Tom V. Matthew sir. Sir has been a constant guiding force and providing advice to NATPAC as a research council member, and also being in earlier area as well, and also as a chairman of regional research council. Sir has initiated several steps to improve the visibility of NATPAC and motivated and recommended us to organize a tech talks series. Amidst of his busy schedule, he has agreed to inaugurate the tech talk series. We are very much thankful to Tom, sir. Thank you, sir. We are also thankful to Dr. Samson Matthew, Director of NATPAC. He has pushed us ahead and being a constant motivational force, and also helped us in implementation of this tech talk series. We would also like to thank the participants who came from the different comprising of different academicians from IITs and NITs, CET, and also we would like to thank the industry research collaborators of NATPAC, and also the department agencies such as NHA, PWD engineers, motor vehicle department, and KSCSTE officials who attended this Tech Talk series. We hope that this Tech Talk series is an immense insight to all the budding researchers in the state as well as in the country. Thank you all once again from NATPAC.
Thank you. Thank you, Dr. Srinivas, for your reference. Mr. Ibn Sam, he is a scientist. His area of research is again the crash like modeling and like crash analysis. He's doing. He's identifying the like black spots, black stretches, and all those areas. He's working again in the surrogate safety measures also that.
Yeah, I remember meeting him a couple of times, so thank you.
Yeah, okay.
I do remember.
Thank you.
And thank you all for the opportunity. I just want to add one thing related to the bandwidth. Again, whoever asked that question, again, you got to suddenly look at AIC cross-validation type of approaches and others. So there are some standard procedures, but if you're interested, just send me an email and I'll be able to share our paper or a little more detail on that one. But just want to thank you for the opportunity to present and share some of our project-related insights.
Thank you so much, Dr. Srinivas. I think good night.
Good night.
Yeah, thanks, sir.
You all have a good day. Thank you very much.
Thank you. Thank you.
Sorry.
Sort of meeting.
No, I was just,
You are there. Okay.
okay. Yeah.
Sir, thank you. So you would like to maybe comment something?
No, I think, yeah, I think the bottom line is like, as I've been telling all, the importance of data that is coming, and for the state of Kerala, NATPAC again has to take a lead in this one, okay, and systematically collect and preserve the data. Analysis can come later. So many opportunities of analysis are there, but data is the key. So I think it's a great thing. Yeah, good. Thank you.
Thank you, Professor.
Bye. So hope you will be giving a nice tea and coffee to your scientists now.
Yes, sir. It is already in its place. It is coming. It will be delivered.